Hi, we are Team 26, presenting Decision Transformer Learning for multi-stock closing price movement prediction. First, I would like to introduce what we're doing. Our project is task-oriented where we participated in the Kaggle competition. It is to predict the final 10 minutes of stock trading in Nasdaq closing cross auction, which can track the closing price movement. The closing price acts as the key indicator to evaluate overall market performances. In general, stock datasets have several properties like volatility and non-stationarity. Many research applied conventional time series regression model and RNN LSTM model. However, the previous approach were not capable of dynamic environments, therefore cannot handle non-stationarity data. The significant difference between simple stock price prediction and this task is that this includes action and it is in discrete time series. We therefore applied reinforcement learning and transformer architecture. For like this literatures, we applied decision transformer, which is the reinforcement learning using transformer architecture to deal sequence modeling problem. The dataset consists of 200 different types of stocks with multivariate time series. The target that we are predicting is the 60-second future move minus the move of synthetic index, where a synthetic index is a custom weighted index of stocks. We did two different processing of data. One was to impute the NA values of stocks that have missing dates and fill far price and near price with minimum for missing values.
Our first approach involved leveraging the power of LSTM networks. We initiate this by employing the basic LSTM architecture consisting of two layers, which with a specified hidden dimension. We further implemented a K-fold LSTM with full folds, effectively creative ensemble of models. Both LSTM model underwent 500 epochs. For the basic LSTM. Our input feature were of a length of 49. This feature were intelligently split into the batch. The final output of this process results in a one-dimensional output with respect to the specified target. Our research placed a significant emphasis on the contribution made by the decision-making transformer. In contrast to a simple transformer that concatenates all feature and process the entire sequence through a causal transformer, our decision transformer introduced a novel approach. Here we divide the info feature into three key components: where to go, state, and action. Unlike the conventional reward, our reward to go encapsulates the summation of future rewards. This crucial concept from RL play a pivotal role in shaping our model's understanding and decision-making capabilities. Each of the components reside in distinct embedding spaces. The deliberate separation is designed to enhance the effectiveness of the learning process. The ultimate goal of our task is minimizing the size of imbalance. By strategically assigning roles to each element, we aim to optimize the learning process and facilitate informed decision-making. We saved every model accuracy to the weighting bias as the chart, and final loss is as the table. Due to the Kaggle submission issue, the test accuracy of decision transformer will be updated in the final report. For next, we are going to compare the result of the validation loss of K-fold, LSTM, and Light GVM. The LSTM loss has converged but not that much be decreased. As you can see in the graph by the data split, they show great difference in the initial loss, but in the test loss, which was about 5.465, showed not that bad score, while Light GVM showed about 5.37. Our training accuracy results are shown in the graph, but the simple transformer and decision transformer model underwent training for 500 epoch each. Decision transformer model outperformed the simple transformer, scoring around 4, which showed that this model is capable of learning intricate pattern and capture complex relationship within the data. To model accuracy comparison, we were to graph, and initial states show the high train loss by the large parameter in the decision transformer, also much smaller train loss converge at the last. From the result analysis, we can conclude that it is necessary to check the test result, but it is helpful to introduce the concept of reinforcement learning through the result of training loss. and can interpret the closing stock task as offline reinforcement learning owing to the relationship between reference price and imbalance size and return to go. Accumulating reward would be helpful to draw a plan of a reference price to minimize the imbalance size.
한 5분